Hello guys, this is Dr. Maharjan here. So this is our very first lecture on fluid statics. The first topic of this course is fluids. So we're going to do fluid statics and fluid dynamics. We're going to spend about 2 weeks. So in particular, we'll be studying pressure exerted by static fluid, also called hydrostatic pressure, Pascal's law, Archimedes principle, and buoyancy. And after doing this topic, you should be able to answer questions such as, what causes the hot air balloon to rise up, which has to do with the physical phenomenon called buoyancy. And also, you have seen this hydraulic lift. This 200-pound person can lift a 4,000 pounds of car, and what causes that? You should be able to answer questions like that. So before we do any details on fluid statics, first you need to know some properties. So first of all, as the name implies, a fluid is a substance that can flow easily. So that's why liquid and gases are of these categories. So liquid and gases are called fluids because they can flow easily, but not the solids. So and the density, in general, density is defined as mass per volume. Mass per unit volume is called density, and its symbol is rho, this Greek letter rho. And its standard unit is kilograms per meter cube, as you can see. So here's the list of density of different substances from solid to gas, and you can clearly see a significance, variation of density from very high to very low. So on this list, gold and mercury has got the highest density, and air and helium they have got the lowest density because they are gas, as you can see. And fresh water has a density of 1,000 kilogram per meter cube. Seawater has a slightly higher density, 1,025 kilogram per meter cube, and our blood has about 1,060 kilogram per meter cube density. And all these numbers will be given when we do solve some numerical problems. So let me ask you a question. A piece of material which with uniform mass density is broken into two pieces. So which piece has the highest density and which one has the lowest density are same? And obviously the answer will be both pieces will have same density, right? Because density is an intrinsic property, and this is true only if the mass is distributed uniformly. So here's an example. Density is mass per volume ratio. So even if this is a bigger piece, its mass is bigger, but volume is also bigger, so that the mass per volume ratio remains constant. And same thing for the smaller piece. So mass per volume ratio for a given substance having a mass uniformly distributed is purely remains constant, and so it's an intrinsic property of the matter. So just like density, how do we define pressure? So pressure is defined as force per unit area acting on the surface. So that's how we define the pressure. So, and its SI unit, our standard unit, is of course newtons per meter square, because force is measured in newtons in standard unit, area is meter square. So newtons per meter square is called the standard unit of our pressure. And you know is however uh, is popular very popular unit of pressure is pascal. Okay, so pascal is basically newtons per meter square. And here's an example of a mechanical, pressure measuring sensor or pressure measuring device. It's basically a spring device, spring connected to a movable piston. And when you apply some force, it produces some compression. And just by measuring this compression, let's say X, you can easily measure the pressure exerted by that force. So because we know that spring force is the pressure force, which is K times X, right? Spring force is pressure K times X. K is the spring constant, X is the compression or elongation. And then you can find out the fluid pressure, so force per unit area, right? Force is given by Kx. So that's the very basic working principle of any mechanical, pressure sensor or mechanical pressure, measuring device. So, so how do you measure the pressure due to fluid? Because here in this whole topic, we are dealing with the fluid, right? So let's say water. So you just need to submerge this pressure measuring device into the fluid. So then the fluid exerts some pressure, right, on this piston, and it produces some compression. And like I mentioned in the previous slide, just by measuring the compression, you can easily measure the pressure exerted by the fluid. And here's an example of the pressure gauge, the tire measuring pressure gauge. And this is the fluid measuring pressure gauge, in any hydrostatic system. So here's the most important part of the fluid pressure to remember. So pressure is everywhere in a fluid. So for example, if you submerge an object into a fluid, say water tank right here at given depth, so this object is acted upon by pressure forces from all directions, not just the downward or not just the side. Pressure forces are everywhere actually. You can clearly see it's acted upon by everywhere from all directions. And here's the three important point to remember in fluid pressure. So first of all, there's a pressure everywhere in a fluid, not just at the bottom or at the walls of the container. The pressure at a given depth is constant, and you can check actually. So regardless of the orientation of this pressure measuring sensor, the pressure is will be you get the same compression at the given depth. If the depth is same, and the third important is point is the the fluid pressure increases rapidly with depth, which we're going to prove mathematically. So here are some subunits and other units to measure pressure. So as I said, newtons per meter square, which is also called Pascal, is the most popular and standard unit of pressure. And it's also measured in atmosphere, atm, a millimeter of Hg, which we'll be talking about that later. And also in real life, however, the most popular unit of pressure is psi, pounds per square inch. Okay. So, what is pressure force then? Once you know pressure, then you can calculate the pressure force acting on the given surface. Because since pressure is force per area, unit area, then pressure force will be pressure times area, right? And that's the magnitude. What's the direction of the pressure force? It's perpendicular to the surface, given surface. So that's how you can calculate the magnitude of the pressure force. Pressure times area on the given surface. So here's some example of pressure. So pressure depends on the area on which the force is applied. Okay, pressure doesn't just depend on the force; it also depends on the area. So here's an example. If you press your finger against the balloon, most probably it doesn't pop up, right? But if you do the same force, if you apply exactly same force but with the needle, you get an explosive pop. And what's the reason? Because with the needle, you're exerting tremendous force, huge amount of force, 100 times more force. So pressure, so in this symbol, you can clearly see right here, area is big, so pressure is smaller, right? But with the needle, even if the force is same, since the needle area is very small, actually it exerts a huge pressure, and because of that, actually, so you're exerting a huge pressure. So next example, so several examples are this bird can easily walk on this lily pad because of this. Look at the structure of his toes. He can easily walk because he exerts this bird exerts very little pressure, and so it can easily walk along the lily pad. So now the main part, so we are interested in deriving the formula which shows how pressure changes with how pressure changes with given depth. So let me show you this derivation. So in this video, I will be solving uh, the formula for hydrostatic fluid pressure. So basically, here's the situation. Let's say you have some pool or lake or ocean. So we like to know how the water pressure or fluid pressure increases with depth, changes with depth. So that's what we want to know. So for example, we like to find the water pressure at some depth here at point, say at point P, and this point P is at the given depth, let's say H. H is the given depth, H or D or whatever. So remember, this water surface is still open to the atmosphere. So here on the top you have still one atmospheric pressure sitting. So we call P0. Okay, and so we like to find the total water pressure at P at the given depth H. So to do that, we first need to do some trick. So let's draw a cylindrical, imaginary cylindrical fluid, you know, with the same height, you know, but any size, any diameter cylindrical, imaginary cylindrical fluid. Okay, then here the fluid adjusts pressure from everywhere, right? It's not just on the top and the bottom, it's from everywhere. But so if you check the fluid pressure in horizontal direction, so the fluid pressure increases with uh, depth, but you can see for each pressure force there is an counterbalancing pressure force from the opposite side. So all the horizontal pressure force will cancel out exactly. But however, let's say this is the pressure force acting on the top of the cylindrical fluid, right? Which is P0A, right? Remember, pressure is force over area. So pressure force is simply pressure times area. So here P0 is just the atmospheric pressure. Okay, it's just the atmospheric pressure, right? So that's why the atmosphere is exerting some pressure force P0A, and at the similarly you have some pressure force acting on the bottom of this imaginary cylinder, which we call P times A. The area of the cylinder is the crossing area is same, right? And there's one more force, right? Is at the center of gravity. Center of gravity, there is a mass times gravity. That's the weight of the cylindrical fluid. Then you can draw a nice free body diagram. Okay, FBD means free body diagram before you solve this problem. So whenever forces are involved, make sure you first draw the nice free body diagram. So your free body diagram will be something like that. There's one upward force, only one upward force acting on the bottom of this cylinder at height h, which is pressure force P times A. And there are two downward forces acting on this cylinder. One, the weight of the cylinder at the center of mass mg, and the pressure force on the top, right? Which is mg and P0A. But remember, everything is in static condition, right? So if you apply Newton's second law, Fy is mass times acceleration. This is zero because there is no acceleration, right? Because everything, this fluid pressure, we are trying to find the hydrostatic fluid pressure. So there's no acceleration, right? So the net force must be equal to zero. But what would be the net force? So Pa, right, which is in upward direction, minus mg minus P0A is equal to 0, right? And so then we will just simplify this equation to find the total hydrostatic pressure at depth, at the given depth h. So pressure times area is then, so just rearranging that, mass times gravity becomes positive, plus P0A also becomes positive, right, on the other side. Now we need to convert this mass into the given variable. Remember, this density, from the definition of density, which is rho, is mass over volume. So mass will be then volume times density. That's what we're going to do here. So mass can be converted to volume times density, and gravity plus P0A PA, right? So we need to do one more step. So volume can be written as area times height, right? The volume of the given cylinder, this imaginary cylindrical fluid, is the cross-sectional area times the height, right? And then you have density of the fluid and gravity plus P0A. So we are almost done. So then here uh, you can factor out this area because area is common. You can factor out. So h rho g plus p0, right? And then area will cancel out. And p is, which is the pressure at the given depth. H is, so I'm just rearranging that, p0 plus h rho g, right? So where p is the pressure, right? Total pressure at the given depth, h. P0 is the total, the pressure sitting on the top, which just happened to be atmospheric pressure in this case, right? Pressure at the top just happened to be atmospheric pressure in this case example. In most of the cases, P0, the total, the top pressure is just the atmospheric pressure. H is the given depth. Depth means measured from the top, and rho is the density of the fluid. It's, remember, density of the given fluid. In this, if you want to find the water pressure, is the density of the water. So you can clearly see uh, pressure changes with pressure just depends on the depth because density of the fluid is constant, gravity is constant, and pressure sitting on the top is constant. So the hydrostatic pressure basically just depends on the depth, nothing else, not shape and size, right? So it's a very important. In general, you can say, finally, you can conclude in general, you can say pressure at the bottom, and this will be in your formula sheet. Pressure, the hydrostatic pressure, fluid pressure at any given depth bottom is pressure on the top, which is usually the atmospheric pressure. If not, you'll have to figure that out. And H rho gravity. So that's our final formula. So there is two types of pressure here, so don't get confused. So if you, so gas and liquid pressure, okay. So if you have a gas in a tank, say propane gas in a tank, the pressure exerted by the gas inside that tank is completely different version than pressure due to the liquid we've been talking about, this topic. The pressure of a gas inside a tank is due to the collision between the gas molecules. There are trillions of collisions per second, inside the gas, and that's origin is, collision. Okay, and that we will study this more in heat and thermodynamics. But the pressure we've been talking about here is hydrostatic pressure. Okay, and that pressure, the origin of that pressure that we want to mention in this topic, hydrostatic pressure due to liquid or fluid, is the gravity. Okay, because unlike this, the hydrostatic pressure is all because of the gravity, because gravity pulls all the liquid down, causing it to fill the bottom. The weight of the liquid is responsible for the pressure, hydrostatic pressure in the liquid. Pressure increases with depth because the liquid below is being squeezed by all the liquid above. Okay, so there's a clear difference between these two types of pressure. Gas pressure in a tank has different origins because of collision, as opposed to the hydrostatic pressure, whose origin is completely gravity. So here's the important conclusion on hydrostatic pressure. So fluid pushes in all directions, not just downward or against the wall, and pressure increases rapidly with depth. And how do you know that? And because of this force. So pressure below at given depth is pressure above, which may be atmospheric pressure or any other pressure. You need to figure that out. Plus density of the fluid times gravity times height. And one more thing to note, which is called gauge pressure. Okay, and so what is gauge? So gauge pressure is actually defined as by this relation. So first you find the absolute pressure using this formula. So once you find the absolute pressure, the exact absolute pressure, then you subtract the atmospheric pressure, and that's called gauge pressure. Because the pressure gauge is many pressure gauge, you know, sensors, pressure gauge measuring devices in real life exclude the atmospheric pressure. It doesn't account for the atmospheric pressure because atmosphere we're all exerted upon by atmospheric pressure. This we are because at the ocean of the gigantic air fluid, fluid is air. So atmosphere is exerting pressure on in everybody, and so how do you find the gauge pressure? Gauge pressure is actually absolute pressure minus atmospheric pressure. So here's an example. So we are at the bottom of this gigantic ocean of air, atmosphere. And this is also even if this is gas or air, the atmospheric pressure has the origin of hydrostatic pressure, okay, not due to the collision, okay, because we're at the ocean of this gigantic air molecules, so, and one atmosphere has that much pascals. Okay, it's about 101 kilopascals, right? In terms of kilopascals, 101 kilopascal is equivalent to one atmospheric pressure because the atmosphere is pressing us from all direction with 101 kilopascals of pressure. So now I'm gonna show you some sample problems just to get started. So here's some example of the existence of atmospheric pressure. So even if the atmosphere is pressing us, with huge force, about 15 pounds per square inch, on any surface on our body, we don't feel that actually. Why? Because say for example on your hand, all right, the pressure force acting here in this direction is completely counterbalance, is completely equal and opposite from the pressure force acting from the other direction. So just like that. So that's why the pressure force exerted by on any part of our body will be completely equal and opposite from both sides. So that's why we don't feel that. Here's some example of the existence of atmospheric pressure. So here this can, right, can be, you can reduce the pressure inside this can by using a vacuum pump, and if you keep reducing the pressure, at some point this can will just implode, right? And here's another example in medical use. So this slip packet kit can be inflated, causing the pressure to increase around the injured hand, which stops bleeding. And here's an example of soda is called a very popular demonstration on atmospheric pressure, So let me show you this demo first. So here's you have a drum. First drum is boiled at one atmosphere pressure, and then you put the cap on it, seal the cap, and then you cool it down. So make sure you cool it down, and then at some point, once you cool it down, the drum will, let's see, implode. So you need to now explain what causes that. Okay, see here, and the same thing here. Soda can. This is called a soda can experiment. Do easily. So first you boil some water in a soda can at one atmosphere pressure. Remember, don't put the seal on the cap. Don't put any cap. So the water should be boiled at one atmosphere pressure. So once the water is boiled, then you invert it. So as soon as you put it upside down in the water, it implodes. So what's the physics behind that? Let me go back to the drum, which is because that's. So first you boil water at one atmospheric pressure, right? So the pressure inside the drum is exactly one atmospheric pressure, right? Before you cool it down, because you let this cap open, so the water boiled at one atmospheric pressure. So then you put the cap, you seal the cap, and then you cool it down. So as soon as you cool it down, some of the water vapor, inside this drum condenses back to water, will condense back to water, and it reduces the pressure. So once you cool it down, the pressure inside this drum is actually less than, slightly less than the pressure, atmospheric pressure outside the drum. And because of this pressure difference, you know, the drum will implode. So that's the main science, main physics behind this. Okay. All right. And there are many other examples. This suction valve hook, works exactly same, because before you stick it against a smooth surface, first you need to push it right with some force. And when you do that, you're creating some partial vacuum, because you're removing some air, right, from the cup, and you're creating some partial vacuum. So reduce pressure inside the cup, and but you have higher pressure, 1 atmospheric pressure outside the cup, and because of the pressure difference, actually you can easily stick it against the wall. And same thing, you can lift the soda by placing a fingertip over the straw. And what's the physics behind that, science behind that is same. So when you do that, you are creating a little slightly less pressure here inside, because it's sealed with your finger. And because of that, you have a low gas pressure, air pressure here, compared to the high atmospheric pressure. Because of this pressure force difference, because of this pressure difference, is enough to lift the mass of the weight of the liquid. Right? So the net force acting on the liquid is that way, and that will exactly counterbalance its weight of the liquid. And we can do some this. I will show you in the sample problems. So the next few more things in this topic is here. So here's an example: different shapes, tubes of different shape, open to the all open to the atmosphere. Is filled with some liquid. So, and once you fill this, even if they have different shape, different size, the liquid always maintains exactly same height. They have to maintain the exactly same height. So what's the science behind that? The science behind that is, since they are all open to the atmosphere, the pressure on the top of this liquid is exactly same. So then if you draw any imaginary line across this liquid, horizontal line, there shouldn't be any pressure difference between any 2 points along this horizontal line. If it does, then liquid would flow from higher to lower pressure to maintain the height. Right. That's the main science behind this. It's also called water seeks its own level. Right. Because, and the main science behind that is because if you draw any imaginary line, there shouldn't be any pressure difference between any 2 points, because this is a static. Everything is a static equilibrium, right? There shouldn't be any pressure difference between any 2 points along this horizontal line. So that's the science behind that. And here's the you know example, so that I will assign. And so barometer works same principle. So barometer is just so people used to measure the atmospheric pressure using a very simple device called barometer. So barometer is basically a test tube, tube, very strong tube, and this container has mercury, is filled with mercury. First, you fill this tube with full of mercury, and then you invert it, and slowly, after some time, slowly the mercury level decreases, and you maintain some height, and you have the completely vacuum here inside this. And this height, just by measuring this height, you can measure the atmospheric pressure. Why? Because if you see this point, the point one, which is open to the atmosphere, and point two on this point, these 2 points must be at exactly same pressure. Why? Because they are exactly in a hydrostatic pressure balance, right? So pressure here and pressure here must be same, right? And otherwise it won't be in static equilibrium. Otherwise, if suppose point two is at slightly higher pressure, then the mercury will flow from higher to lower pressure until it maintains the equal pressure. And people used to measure the atmospheric pressure using this barometer technique. Just by just by measuring this height of the mercury level, you can measure the atmospheric pressure. So if you measure the height of this mercury column at sea level, it will be exactly 760 millimeter, 76 centimeter. Okay, so that's the equivalent atmospheric pressure. But however, liquid water is a very light liquid, much lower density compared to mercury. If you use water instead of mercury, you would need 10 meters, 34 feet height. So it's not very practical to do this barometric measurement in water. So you need some heavy liquid like mercury. And here's some example problems that I will show you in example problems.